Hello. In this lecture we will explain what is diffie-hellman. So IPsec is a suite of protocols that allows for traffic confidentiality, integrity, and authentication. Confidentiality uses the encryption concept we talked about in the previous lecture. Integrity and authentication uses the hashing functions that we talked about in the previous lecture. There are two types of IPsec frameworks, IC version 1 and IC version 2. We are going to start by talking about IC version 1. There are two phases of IC version 1, IC phase 1 and IC phase 2. So in IC phase 1, the two gateways, we are going to call firewalls. Those are the devices that terminate VPN, or we can call IC gateway. The two IC gateways would negotiate keys to protect the communication. The keys that are negotiated would allow the two devices to communicate to each other numbers. Based on those numbers, they would arrive to a common shared secret key. And if anybody is eavesdropping on the conversation and sees those numbers getting exchanged, they will not be able to figure out what is the shared key that was derived from this conversation. So, even though they see the communication in clear text, they cannot arrive to what shared secret key was produced from the outcome of the exchange. So, this phase is the asymmetric phase of the communication. In phase 1, the two gateways agree on what type of encryption they're going to use. They would agree on what type of hashing and what type of pseudo-random function they will use. Encryption is used to scramble data while hashing is used to ensure that nothing changed in transit. Example of encryption are triple DES and AES. Example of hashing algorithms are MD5 and SHA. The two gateways authenticate each other in this phase, phase 1, using either pre-shared keys or certificates. And then once they finish that phase, they will have keying material or encryption keys that can get used to exchange the symmetric phase of the communication, which is phase 2. Phase 2 is called quick mode and is used to encrypt data between the two gateways. And that's the last phase of the communication. And we are going to see how this works. So what is diffie-hellman? Diffie-hellman allows two parties to exchange numbers publicly and run calculations to derive a shared secret key. Each entity individually arrives to the same shared secret key. If someone is eavesdropping on the conversation, they will see the keys exchanged, however, they will not be able to figure out the shared secret key. The components of the diffie-hellman are two numbers, a prime number and a generator number. Those two numbers are either based on the Oakley protocol, or elliptic logarithm. We will focus on the Oakley protocol. So, when the two IC gateways want to communicate to each other, they agree on which diffie-hellman group to use. The group agreement is the one that determines what will be the prime and generator numbers used in the exchange. Those are well-known numbers and are documented in the RFCs. They agree on which diffie-hellman group they will use for the exchange. Based on this agreement, both sides will know what is the prime number and generator number that will be used. In our example, P, prime number is equal 179, and G, generator number is equal 19. The firewall on both sides would start off with those two numbers. The firewall on the left will pick a private key, like we saw in asymmetric encryption. Using the private key, the gateway is going to run through a formula. And this formula is G, which is the generator number. The generate number exponent of the private key mod P. This will produce the public key. So firewall A, the initiator, has calculated the public key. It is going to send that public key to the other side. The other side selects a private key as well. In this case, the firewall B, or the responder selected B equal 5. 5 is its private key. And it's going to run the same operation except for that it is going to use its own private key. Then it is going to arrive to its own public key. It will send the public key to the other firewall. What we have so far is the initiator firewall sends the public key, its own public key, to the responder firewall. And the responder firewall sends its own public key to the initiator firewall. Then both sides would run a calculation. They would take the public key of the other side and run it through this formula. The formula is public key of the other side mod p to the exponent of its own private key. Firewall A runs this calculation of b mod p to the exponent of A, and the responder runs a mod p to the exponent of b, its own private key. And if we look at those two calculations, they are pretty much equal. And if somebody, an eavesdropping and listening to the conversation, they will know that they are using the Diffie-Hellman group. The Diffie-Hellman group is publicly known. They are going to see the two public keys used by Firewall A and Firewall B. But they don't know what is the private key of both sides. In order for them to decrypt the traffic, they will have to know the shared secret. Because whatever gets encrypted by the private key will get decrypted by the public key. Because of this, if I don't have the private key, I will not be able to decrypt the traffic. And so I need to know what is the private key of both sides so that I can be able to decrypt the traffic. How can an eavesdropper determine what is the private key of both firewalls? They don't have any option except to run a brute force or compare the number against hash tables. And in this hash table, they can look up the number of the public key and figure out what the private key is. Or they can run a brute force and brute force the keys using one guessed number at a time. They try the numbers until they arrive to the private key. Because they see this is 57, the generator to the power of 1 mod 179, mod the public key. Power of 2, power of 3, exponent of 2, exponent of 3, and so on. They would do this until they find the public key, which is 57. So this is called brute force, or they can look up a hash table to determine that if public key is 57, then private key is 3. So in this example we are using very small numbers. In this case, we are using 8 bits. The Oakley-based, Diffie-Hellman groups that are used, uses much larger numbers. For example, group 1 is 768 bits. Group 2 is 1024 bits. Group 5 is 1536, and Group 14 is 2048 bits. So those are pretty large numbers that would make the brute force difficult to do. It's going to be pretty difficult for somebody to break in. It will be difficult to figure out what the private key is, and then decrypt the rest of the communication. So group 1, 2, 5, and 14 are using logarithmic math. Group 19 and Group 20 are using elliptic curve logarithmics, which basically uses the same concept, however, it calculates the shared secret using elliptic curve. The elliptic curve method is preferred, because it requires less memory and computer power, and it's infeasible to break it. 168 bits of the Diffie-Hellman is equivalent to 1024 bits of elliptic curve operation. 256 bits is equivalent to 15,360 bits. It is preferred to use Group 19 and Group 20, which uses elliptic curve algorithm. We will talk more in the next lecture.